Hey Kipsters, today we're going to be working on Module 4, Lesson 28, another computational method of solving a linear system. Yesterday we were learning, we got some exposure to the nature of solutions to linear equations. We found out that a system of linear equations could have no solution, one solution, or infinitely many solutions. Today we're more so going to be focusing on what's called the elimination method. The elimination method. Go ahead and find that note sheet in your packet. It should be on the back of your opening exercise. And let's take some notes around the elimination method. Throughout this lesson, you're going to be asked to verify that your solution is correct by graphing your system and then comparing your point of intersection to your solution. We're going to use what we know about properties of equalities and equations and expressions to eliminate either our x or our y to solve for a variable and then substitute that variable. So let's put that in words. The elimination method. All right, let's take some notes on the elimination method. The elimination method is literally going to eliminate either an x or a y from your system to solve the remaining variable. You're then going to use the variable that you solved for to substitute back into the equation to create your solution. All right, let's look at some examples. Let's go ahead and write these down on our paper. So let's look at the solution, the system of linear equations, y equals 3x plus 5 and y equals 8x plus 3. Describe how you would solve this system algebraically. Well, since both sides are equal to y, I should in fact be able to say that 3x plus 5 equals 8x plus 3, okay? And begin to move my x terms to one side and move my constants to another side to find out that x is actually equal to 2 over 5. So I could get down to one term. That allowed me to eliminate the variable y. Well, let's look at the second system of equations. Let's take a look at this second system of linear equations. If I wanted to describe algebraically how to solve this, and I wanted to use the elimination method, I notice that I have a term in y and a term in 2y. If I substitute my first expression into the second equation in place of y, I've actually eliminated the variable y. Okay, so then this then transforms the equation to say 14x minus 4 minus 4x equals 10. Okay, we'll reduce down to, I can combine these like terms, 14x minus 4x, so I get 10x minus 4 equals 10. Move over, so I'm running out of space, so 10x minus 4 equals 10. I could isolate my variable by adding 4 to both sides, and I get 10x equals 14, divide both sides by 10. So x is actually equal to 7/5. Because 14 divided by 2 is 7, and 10 divided by 2 is 5. Let's look at another example. Look at this system of linear equations. Describe algebraically how you would solve. Since both equations are equal to x, we could write 6y plus 7 equals 10y plus 2, which would eliminate the x variable. In this lesson, we're going to learn a method for solving systems that requires us to eliminate one of the variables, but in a different way from the last lesson, So let's find example number 1. In example number 1, what do you notice about adding the equivalent expressions to solve the following system by elimination? In other words, looking vertically, are there any like terms that do something special when you add them? Well, I notice when I do 6x plus 2x that I'm going to end up with some bigger x's. But when I do negative 5y plus 5y, I eliminate my y's from the problem. So I'm left with no y's. Now that's equal to a 21 minus 5, which is going to leave me with 16. Because I no longer have y's in the problem, my goal is to solve for x. So I'm going to divide both sides by 8. And I get that x is equal to 2. Once I get an x of 2, I then use x to substitute. You can pick either equation that you want to substitute into. My default is going to be the first equation. So I'm going to write the first equation down like I've been given, 6x minus 5y equals 21. And I'm going to substitute in x. What does y equal when x is 2? So I have an x and I have a y. What does that tell me about my problem? This tells me that the solution set for this system is 2 and negative 9 over 5. Let's say I wanted to verify that this is actually the solution to this system. I could sketch a graph of my system of equations. So this line represents 2x plus 5y equals negative 5, and this line represents 6x minus 5y equals 21. And I notice that my point of intersection is at an x of 2, right now. Sorry about that rain that came in the room, guys. An x of 2 and a y of negative 1 and some change. Ask yourself how many 5s go into 9. 1 and some change, almost 2. Example number 2. Example number 2 asks us to solve the following system by elimination. And this example is not as obvious which variable to eliminate, but it'll become more obvious as soon as we multiply the first equation by 2. So let's do that. We're going to take our first equation, pull it out, negative 2x plus 7y equals 5. And I'm going to multiply the entire equation by 2. How does that change my equation? Well, each term is multiplied by 2, so a negative 2x becomes a negative 4x, and a 7 becomes a 14y, and a 5 becomes a 10. So now the new system of linear equations I'm evaluating is negative 4x plus 14y equals 10, and 4x minus 2y equals 14. So now that we have this system, it's clear to us that we're going to add negative 4x plus 4x, and which variable will be eliminated. When I add them, my x term is going to be eliminated, and we can then begin to determine the solution to this system. So I'm going to continue to simplify. I'm going to use y to substitute into the equation. For purposes of modeling, I'm going to choose the second equation this time. 4x minus 2y equals 14. Written it like I've been given, then I'm going to rewrite the problem, except this time wherever I see a y, I'm going to substitute in the 2 I just solved for. Using the order of operations, I handle this multiplication. Negative 2 times 2 gives me negative 4 equal to 14. When I'm trying to solve for x, I need it alone, so I'm adding 4 to both sides. I'm going to divide 4 on both sides, and x is equal to 18 divided by 4, which reduces to 9 over 2. What's the solution set for this system of equations? The solution set for this system of equations is 9 over 2 and 2. We can verify our solution by sketching the graph. So this is a graph of both equations, and you'll notice that they intersect at one point, particularly an x of 9 over 2, which is 4.5, and a y of Continuing with the work we've been doing with elimination, we're going to solve the following system by elimination. In this case, just like the last case, when it's less obvious to determine which variable to eliminate, that means we have to transform one or maybe both of our equations. I could multiply my first equation by a -3 and my second equation by 7. How would that change my problems? So again, I'm going to multiply my first equation by -3 and my second equation by a 7. How does that change my equations? Well, it's going to change my first system to become -21x plus 15y equals 6. And my second equation will become 21x minus 21y equals 49. Because I've multiplied both of my equations, I can now easily identify which variable will be eliminated. Which variable am I eliminating? I'm going to add these together to eliminate my x term. So I do that, and I'm going to be left with 15y minus 21y, even with -6y equals 6 plus 49, 55.